Okay, so this video is going to look at more detailed aspects of the different types of forces that you can encounter and will encounter in different problems and on the AP exam. First one looks at mass and weight. So a lot of people think that mass and weight are the same thing, but they're not. Mass is really the amount of material in an object, and weight is simply the force acting on the mass. Okay, so your mass is fairly constant. It's the amount of material on you. Your weight is that force acting on your mass. Okay, so again, little conversions here. A newton is about, a little less than a quarter of a pound. Okay. All right. So what are the weight in newtons and the mass in kilograms of a 90-pound gymnast, a 150-pound professor, and a 240-pound football player? So just do your conversions. Okay. Just to get you an idea of where things are at. Okay, you can get the weight first if you know the weight in pounds. Just do the conversions to get to newtons. And then because you know the weight in pounds, you can actually convert it to kilograms as well. Okay. That won't be probably so much on your AP exam, but they're good pieces of information to have. Okay. So again, got to kind of understand what's going on here. If you look, roughly 4 times more weight in newtons than in pounds. Okay, so if you messed up and said that a 90-pound gymnast has a weight of 900 newtons, probably know that that's not close to the right answer. Okay, the apparent weight really looks at how when you're like in a state of what's called free fall, if you're falling and there's nothing to slow you down, you're kind of in an elevator that's falling, or if you're in a roller amusement park ride that just falls straight down. Okay. The apparent weight, if it's slowing you down, there's a force pushing you up. There's a little bit of a normal force there. Okay. So when we look at this, as you go upward, okay, the net force is going in an upward direction, and you feel heavier because the thing is lifting you up. Okay, so the upward force is your weight plus mass times your acceleration. Okay, so you feel heavier when an elevator goes up because there's more force pushing you upward. Okay, let's take a look at this problem here. So Andre's mass is 70 kilograms. He's standing on a scale on an elevator that is moving upward at 5 meters per second. As the elevator stops, the scale reads 750 newtons. Before it stops, was the elevator moving up or down, and how long did it take the elevator to come to rest? Okay, so let's figure out his actual weight first. His actual weight is 70 kilograms times 9.8 meters per second. So his actual weight is 686 newtons. That's how much downward force is acting on Andre at all times. His actual weight. Okay. Now, it's kind of a go-between step. Okay. But now that we know that force, okay, that's going to help us along with this 750, figuring out if the elevator is going up or down. Okay. Now, if we look at this, we know his weight is 686 newtons. So his weight is 686 newtons. He feels like he's weighing 750 newtons, and his mass is 70 kilograms. So we can take the difference in force to get our net force divided by the mass to get our acceleration. Okay. So 750 minus 86 divided by 70 gets us an acceleration of 0.91 meters per second squared. Positive acceleration. So because of that, okay, the elevator is slowing down. Okay. But the acceleration is upward. Okay. The acceleration is not going up, but it's still going in a downward direction. Now the stopping time. We know its initial speed. Its initial speed is moving downward at negative 5 meters per second. How do we know that? It tells us right here. Okay. So it's moving downward at initial speed of negative 5 meters per second. Velocity y final is 0. So we know our acceleration, because acceleration is change in speed over time. Rearrange it to solve our change in time is equal to change in velocity over acceleration. So we end up with 5 divided by 0.91, and it's going to stop in 5.5 seconds. Okay. So the elevator is moving downward. Okay, go back and look at it if you need some help. Okay. So again, it's coming to it's moving down, and then it comes to rest. You feel heavy. Okay. If you're weightless, okay, what that means is it feels like your weight going down, and you're really not being supported, and you're kind of just floating. Okay. I'm going to show you what this looks like in this airplane. This is called the vomit comet. Okay, what happens is it goes up, you get pushed to the floor. This is happening as the airplane comes back down a parabola. So this is a video demonstrating the vomit comet. So now they're going upward in the parabola, and they're on the ground. Watch what happens here.
Some specialists thought our internal organs would just fall apart and we'd drop down dead, or float away dead anyway. So the Americans sent the whole menagerie of animals into orbit to see what it would do for them, and they all survived.
This is happening because now the airplane is going down the parabola, and then they float.
That wasn't really the point. The point was oh God. The point was, would a man be able to do something useful in zero gravity? For example, operate a spaceship. So what they did was they sent a trained chimpanzee called Ham into orbit on the 31st of January 1961. Ham had been trained to pull a series of levers in response to flashing lights.
The red lever.
Forward a little bit here.
Oh, it's a parlor. Sorry.
And then when they get the bug, they go crashing out.
And this is where this child's game comes in, because it's a very, very similar thing. What happens in?
Astronauts spend a lot of time training in that to get an idea of what weightlessness will feel like. You can find lots of YouTube videos on weightlessness. All right, then we look at the normal force. Okay, so again, the normal force goes perpendicular to the surface. Okay. So we have a book sitting on the table. Press down with a force of 15 newtons. What's the normal force acting on the book? Okay, so we have the weight going down and a force going down. The net force is 0, so the normal force has to balance out both those forces of the weight and the force applied. Okay, so if we know you're applying a force of 15 newtons. Okay, and we know the mass of the box or the book. So if we know the mass of the book, we can figure out the weight of the book. Okay, the weight of the book is simply the mass times acceleration to gravity. So our normal force has to equal the mass of the weight. The normal force has to equal the force you apply plus the weight of the object. So 15 is the force you apply. 12 is the weight of the object. 15 plus 12 is 27 newtons. So the normal force has to be 27 newtons. If it was larger, the normal force was larger, then the weight combined, then the force of both, it would fly. Okay. Now, if we look at this, okay, the force is on an incline, you should be thinking, okay, weight goes straight down. Okay. We have the force of this weight in the x direction, for the force of the weight in the y direction, if it's on a ramp like this. Remember, the incline of the ramp is the same as the angle between this line that goes kind of straight down from the normal line to the weight of the object. Okay. The normal force is always perpendicular to the surface, and weight always goes down. This is a common mistake on the AP exams. Weight goes straight down, normal force goes perpendicular to the surface. Okay. So the skier goes down a slope. Okay. We're going to see if we can figure out the skier's acceleration if we know the angle of the slope. Okay. So it's accelerating downhill. Okay. Now some of you might think we don't have enough information, but we do. Okay. So we're going to look at how to figure this out, figure out our net force going down, and thus being able to figure out our net acceleration. Okay. But if you look at all this, okay, second law, change in force is weight, the weight times the normal force, and the x in weight times normal force in the y. Okay. We have the x, okay, because n points directly in the positive y direction, that's the normal, okay, and there is no horizontal normal force, it's in the y direction. Okay, so now we can figure out the y components first because we know the weight angle. Okay, so the acceleration of the object, if you think of it going back to here, we know the acceleration in this direction is 9.81. Okay, and we know this angle is 20 degrees. So if we know this angle, if we know this acceleration is 9.81, we know this is 20 degrees, we can figure out the two accelerations in both directions here, just by using sine and cosine. Okay. The x direction is the opposite side. So ax is equal to g sine theta, again. Why? Because we know that this angle is 20 degrees, and we're looking for this side here. So the sine of the angle is equal to the opposite side divided by your hypotenuse. So the sine of the angle is equal to 9.81 divided by the hypotenuse. Excuse me. Sine is equal to this divided by hypotenuse. Okay, you get your acceleration to be 44 meters per second squared. So again, we know this is 20 degrees. This is 9.81 meters per second squared for the acceleration. So this acceleration, this leg of this acceleration, is going to be the acceleration here, causing this net force. Okay. Okay. The next one is friction. Say we have forces of friction that act in the opposite direction of how you move. Okay, static friction keeps something in place, kinetic friction makes it move. Okay, so if an object isn't moving, the static friction is equal to the force that you're applying. Okay, this is a case of static equilibrium. Okay, now there's a fraction component called the coefficient of friction, is mu. Okay, so when you look at if you kind of rearrange this equation, you get mu s is equal to Fs max divided by your normal force. Okay, it's a fraction relationship. Okay. So again, going back to the boxes, the harder she pushes, the harder the box pushes back. Okay. But if she can push hard enough, the box will slip and start to move. Okay, that maximum force is what's called your FS max. How much you can actually apply to it before the object starts to move. That's your FS max. The FS max is divided by your normal force. Will get you the coefficient of static friction. Okay, so if you can push something and right before it starts to move, that's your FS max. Your force static maximum before it starts to become force kinetic. Okay. It opposes motion. Okay. And it's the net force is 0 because the object is still not moving. Okay, so the static friction kind of fluctuates until it gets to a point where you can overcome it. And then once it moves, then you get this coefficient of what's called the coefficient of kinetic friction. Okay, but if your net force is 0, once you get it to move, your force applied is equal to your force kinetic. Okay. If it's moving at a constant speed, if you can get it moving at a constant speed, the force you apply is equal to the force of friction because it's moving at a constant speed, Newton's first law. And you can use the same basic coefficient of friction equations. The coefficient of kinetic friction divided by your normal force gets you your coefficient of, your force of kinetic friction divided by your normal force gets you your coefficient of kinetic friction. Okay. Rolling, same basic idea. There's a lot less friction in rolling friction because there's a lot less surface area of contact. Okay. So the coefficient of static friction, if you look at all the coefficients, has the greatest coefficient, followed by kinetic, followed by rolling friction. Okay, give you an idea here. All right. And you notice there's different coefficients depending on what surfaces come in contact with each other. But again, the coefficient of kinetic friction changes depending on how much force you apply until it hits that max point. Okay. Coefficient of kinetic friction, okay, if an object's moving at a constant speed, you can figure out the coefficient of kinetic friction because it's going to be balanced to the force that you apply. Okay. When an object's not moving, it's static friction. When an object is sliding relative to the surface, it's kinetic friction. When the object's rolling along the surface, it's rolling friction. Some problems you'll have to take into account friction, others you will not. Okay, example here. All right, so we have a coefficient of friction. She then pushes the sofa at a steady 0.4 meters per second across the floor. How much force does she apply to the sofa? So now we know her mass of 32 kilograms. So we know our weight, and we know then that the normal gets balanced out by our weight. We know that this has a coefficient of kinetic friction of 0.08 between the slippery discs and the floor. Okay, so if we know that coefficient of kinetic friction, we can figure out the force applied in the force kinetic. Okay, now we've got our free body diagrams. Okay, we know that the force in the x direction and the force in the y direction, the net force has to be 0 because she's moving at a constant speed. Okay. Now, we know that the normal versus minus weight is 0. Okay, so weight is mass times gravity. So normal could be equal to the same as mass times gravity. Okay, so we're going to figure out the force applied. Okay, using Fk is equal to mu Kn. Okay. So we know the normal is the same as the weight of the object because it's on a level ground. So 32 kilograms times 9.81 gets you the weight of the object, mass times gravity, times the mu, 0.08 that we know, gets our force kinetic of 25 newtons. Okay, so that means this force is 25 newtons. But because it's moving at a constant speed, we know that that force is also equal to the force kinetic of kinetic friction. So it's 25 newtons. Okay, go back to the diagram here. So now we figured out this weight. Okay, the weight is equal to the normal force. Okay, so when we got the normal force, we knew the coefficient of friction. We can use that to solve for Fk. And because it's moving in a constant speed, there's no net force. Our Fk and our F applied are the same. Okay. Now, all surfaces are rough on a microscopic scale, so they're all going to have some levels of friction. Okay. I'll show you. Just take a look at this one. Okay. Another sample problem. Car is traveling at 20 meters per second in a distance of 50 meters. Okay, we have the coefficients of friction. Okay, we're going to figure out if they slide off the seat or not. I want you to solve this for class. All right, the next one is drag. Again, it's like it's air resistance of a falling object. Okay, because you have to move through air, and the reason, just that fact that you're moving through air is going to put some air friction drag on an object. Okay, this is the area of drag. You don't necessarily have to worry about this. Okay, but understand the greater the area, the greater the drag. And if you think about that, you should know this, that a bigger vehicle has a bigger cross-sectional area. It's going through more air. It's going to have more drag. Okay. Then drag also applies to this thing called terminal speed or terminal velocity. That's the fastest speed an object can fall. Okay. At that point, at terminal velocity, okay, the acceleration due to gravity is balanced by the acceleration pushing up from the air resistance for the drag. This doesn't mean this object stops. It just means it stops accelerating so it hits its maximum speed. Okay, so you can figure out the terminal speed of a skydiver. Okay, bigger the area, bigger the drag. Okay. And from this you can figure out the drags, and then you can figure out how fast an object's terminal velocity is. And we get that the man's terminal velocity is a lot bigger than the mouse's, because it takes a lot more. There's a lot more drag. It takes a lot longer to slow down the man than it does the little teeny tiny mouse, because of the mass component here. Okay. So just a quick little thing. Weight is just the force down. Normal force is the force pushing up from the surface. Tension from a spring or a rope. Static friction, the friction keeping something in place. Kinetic friction, the friction that opposes the motion once it moves. Drag is that air resistance. Okay, and it just kind of puts everything together. This is in your textbook, Synthesis 5.1. That's the end of Unit 2, Part 3. There's a lot of information here. Make sure you go through it a couple different times and be ready to ask questions in class. We'll see you in class.